हितम समाज हितम
Good evening students. Today we will discuss isomerism in organic compounds. First of all, existence of two or more compounds with the same formula but different physical and chemical properties is known as isomerism. Okay, you know all these fundamental concepts. Isomerism is again classified into two types, structural isomerism and stereoisomerism. Again in this structural isomerism we have chain isomerism, positional isomerism, functional isomerism, metamerism and tautomerism. Again in this stereoisomerism we have configurational isomerism and conformational isomerism. Again in this configurational isomerism we have stereoisomerism and geometrical isomerism and optical isomerism. Okay, first we will see some important examples in this isomerism. No need to discuss all, just briefly we will focus on important examples. First of all, you know what is structural isomerism. Existence of two or more compounds with this formula but different structures are called structural isomers. Again in this we will see chain isomerism, or it is also known as skeleton isomerism. So if you take this chain isomerism, compounds with the same formula but different arrangement of carbon atoms in chain are called chain isomers. And one important point is that to exhibit chain isomerism, alkanes and alkenes contain minimum of 4 carbons, whereas alkynes should contain minimum of 5 carbons, that you know. Then if we take C4H10, this is butane, an alkane. So how many possible isomers for this one? First I write this is bond line model, already you know that. Or if you take elaborated structure, first you write 4 carbons, then the remaining valencies are satisfied with hydrogen atoms. So around this to get tetravalency, 3 more hydrogens, here 2 hydrogens, 2 hydrogens, 3 hydrogens. This has no branch, straight chain, that is why this is called N-butane. And I shift one carbon to this middle carbon, then it becomes CH3, CH3, here CH3, and this is known as isobutane. Iso, if it is like fork like structure, fork like means if there is a methyl group at second carbon from one end, it looks like a fork, then it is called isobutane. So for butane there are 2 chain isomers, N-butane and isobutane. And you know what is the IUPAC name of this one? In IUPAC naming system we should not use this N, simply it is butane, whereas IUPAC name of this one is 1, 2, 3, 2-methyl propane. Then if we take next homologue of this one, C5H12, and this has how many isomers, chain isomers? 3. One is N-pentane and another one is isopentane and another one is neopentane. This is neopentane, and you try to write IUPAC names of these isomers. Then coming to next butene, similar way you can write structures. For butane, how many structural isomers are possible? That is, chain isomers are possible. One is this is N-butene and another one is isobutene. This one, N-butene, isobutene. So, 2 chain isomers are possible for butane. What is the molecular formula? C4H8. Now, if you verify, number of carbon atoms and hydrogens both contain same number of carbon, same number of hydrogens, but here they differ in arrangement of carbon atoms in chain, that is why these are called chain isomers. Now, when it comes to alkynes, there should be minimum of 5 carbons to exhibit chain isomerism, that is C5H8 alkyne 1, 2, 3, 4, 5. Then this one. So, what is the name of this in common naming system? N-pentyne, and this is isopentine. Is there any other possibility? If I write this carbon at this carbon, tetravalency of carbon is violated. Around this carbon there will be 5 bonds, so we cannot write. So, how many isomers are possible for pentyne? That is N-pentyne, isopentine. Okay. Come to the next isomerism, that is positional isomerism. Compounds with the same formula, same functional group, but differ in position of functional group are known as positional isomers. For example, if we take C3H7Cl, or first we will start with alkene. Okay, C4H8 example. This is butane. First I write 4 carbon atoms, then this is an alkene, so there should be a double bond. So, I place double bond here, then here it is CH, CH2, CH3. Now, in numbering 1, 2, 3, 4. So, there is a double bond at first carbon, that is why this is but1ene. Now, I will shift this double bond to this second carbon, then it becomes but2ene. Similarly, another example, we will take butane, that is C4H6, butane. So, here I am writing in bond line model but1ine. Now, I will shift this triple bond to this carbon, then it is but2ine. What is the difference here? In positional isomerism, root word of isomers will be same. If you see IUPAC names of chain isomers, in chain isomers root word will not be same, root word will be different. Whereas in positional isomers, root word will be same, but, like this. Then another example, C3H7Cl, this is propyl chloride. So, here this is how many carbons? 1, 2, 3. Chlorine is attached to this carbon and common name of this one is N-propyl chloride. And what is the IUPAC name? 1, 2, 3. Chlorine is attached to first carbon. Then what is the IUPAC name of this one? 1-chloropropane. Now, we will shift this chlorine to this middle carbon. Then it becomes its isomer. What is the name of this one? Isopropyl chloride. This is common name, isopropyl chloride. Now, what is the position of this second, this chlorine at second carbon? So, what is this one? 2-chloropropane. Now, observe this root word. Here it is prop, here also prop, but only the difference is in position of a substituent, that is chlorine. So, these are positional isomers. Like this, You can check with other compounds like C3H7OH or it is C3H8O. Its formula is also written as, if it is alcoholic structure, C3H7OH. The same way you can write two alcohols, N-propyl alcohol and isopropyl alcohol for this one. Then you see what are the IUPAC names of those alcohols. Now coming to the next one, functional isomerism. Molecules with the same molecular formula but differ in nature of functional group are known as functional isomers. Here we have different sets of functional isomers. For example, if we take CnH2n plus 2O, with this general formula, two types of compounds are possible, alcohols and ethers. Molecular formula is same, but they differ in functional groups. The functional group of alcohols is OH and ethers is O, ethereal oxygen, O. Then we will see examples. Let N is 2. Then what is this one? C2H6O. One structure is alcoholic structure. So I write CH3CH2OH. Functional group of alcohols is OH. Then another one we have to write ether structure. So ether oxygen will come in the middle of two carbons. That is why CH3OCH3. Now what is this? Common name of this one is alcohol, common name is ethyl alcohol. And you know IUPAC name, eth plus En plus ol. Two carbons, single bond between carbons, and functional group is OH. To indicate alcoholic functional group, secondary suffix is ol. So ethanol. Now this ether is two methyl groups attached to oxygen, that is why it is dimethyl ether. And IUPAC name of this one is, general IUPAC name of ethers is alkoxyalkane. So in this way, methoxymethane. Methoxymethane. So this is the IUPAC name. Now what is the difference here? They differ in nature of functional group. Now another example we will take. C3H8O. How many alcoholic structures are possible? Let first I write 3 carbons. I place OH at first carbon and OH at second carbon in another structure, and third structure I write like this. So 3 structures are possible, 2 alcoholic structures and 1 ether structure. So if we take relation between these two, already you know these two are positional isomers, whereas these two are functional isomers. Similarly, these two are functional isomers. So what is this alcohol? N-propyl alcohol. This alcohol, isopropyl alcohol. And this ether, this is ethyl group, this is a methyl group, ethyl methyl ether. And IUPAC name, the name of the alkyl group which has less number of carbons is taken as alkoxy. So here methyl plus oxy, methoxy, remaining 2 carbons. So what is the IUPAC name of this one? Methoxyethane. Now these two are positional isomers, these two are functional isomers. Similarly, these two are functional isomers. Or you can note down like this, 1, 2, 3. So the isomerism between 1 and 2 positional, 1 and 3, 2 and 3 functional. like this. Now, we will take next isomerism, that is metamerism. Compounds with the same formula, same functional group but differ in nature of alkyl groups attached to functional group are known as metamers. Same formula, same functional group but differ in nature of alkyl groups attached to functional group. Nature of alkyl groups attached to functional group. Generally, this metamerism is shown by ethers, thioethers. Thioethers have a functional group S in place of oxygen, sulfur, that is why it is called thioether. Ketones, thioketones, this is thioketone. And secondary amines, esters, these compounds show metamerism. Now, we will see some examples. I will take with C4H10O. Now, I want to write only ether structures now. Let first a methyl group, then remaining carbons in another alkyl group. Next, I will take like this. Next, 2 carbons in one alkyl group, 2 carbons in another alkyl group. Now, if you observe this molecular formula, all these 3 compounds have same molecular formula, that is C4H10O. Functional group is also same. Then what is the difference? Here what is this group? Methyl group. Here it is N-propyl group. What is this? Methyl isopropyl group, and here 2 ethyl groups. So, all these 3 have same functional group, same formula but differ in nature of alkyl groups. So, what type of isomers these are? Metamers. Then we see IUPAC names of these 1, 2, 3. This is the parent chain. Here this is the parent chain 1, 2, 3. Let here it is the parent chain. Then this alkyl group has less number of carbons, that is methyl. So, a prefix is used methyl plus oxy, methoxy. Then what is the parent? 3 carbons and a single bond. So, methoxypropane. Now, you see this one, this methoxy group is attached to first carbon, that is why it is called 1-methoxypropane. Now, come to the next one, similar, but the difference is this methoxy group is attached to second carbon, that is why IUPAC name of this one is 2-methoxypropane. Now, coming to this one, this is ethyl plus oxy, ethoxyethane. This is one example for a metamer. Now, I will take another example. Let C4H11N, that is an amine. Or we will see in general how many isomers are possible for these compounds. Okay, we will take C4H10O. Now, we will see total how many structural isomers are possible with this one. It is in accordance with CnH2n plus 2O. So, with this what can be written? Alcoholic structures and ether structures. Now, first we will write alcoholic structures. This is one alcohol, you see 4 carbons. I am writing in bond line model, there should not be any confusion, you have to practice bond line models. Now, if you take common name of this one, N-butyl alcohol, and what is the IUPAC name of this one? 1, 2, 3, 4. 4 carbons root word but single bond N and secondary suffix for alcohol is ol. So, first carbon, this is butane 1 ol. Then another example we will take, another structure, possible structure. Now, we will shift this OH to the second carbon. 1, 2, 3, 4. Alcoholic group is attached to secondary carbon of butyl. That is why it is called secondary butyl alcohol. Now, what is the IUPAC name of this one? 1, 2, 3, 4. Second carbon OH. So, what is this one? Butane 2-ol. Now, I will change the arrangement of carbon atoms in parent chain. So, we get one structure like this. I am shifting this carbon to this middle carbon. Then this is now what is this one? At second carbon from one end there is a methyl group. It is like a fork. That is why what is this one? Common name of this one is isobutyl alcohol. Now 1, 2, 3. At second carbon methyl group is there. So, IUPAC name of this one is 2-methyl butane 1-ol. Now, what I do? I will shift this OH to this second carbon. Then we get another possible structure OH here. 1, 2, 3. Now, what is this? Here this carbon is surrounded by 3 other carbons. So, it is a tertiary carbon and total number of carbons in this one 4. That is why common name of this one is tertiary butyl alcohol. Now, what is the IUPAC name of this one? 2-methyl butane 2-ol. So, these are the possible alcoholic structures. Now, we will see ether structures possible. Just now we discussed what are the ether structures possible with this formula. One is 1-methoxypropane and another one is 2-methoxypropane and another one is ethoxyethane. So, if you see common name of this one, this is methyl N-propyl ether and IUPAC name of this one 1-methoxypropane. This is isopropyl group. So, common name of this one is methyl isopropyl ether. And IUPAC name of this one 1, 2, 3, that is 2-methoxypropane. Now, coming to this one, common name is 2 methyl groups, that is why it is diethyl ether. Then ethoxyethane, right. So, these are the possible structural isomers with the molecular formula C4H10O. Then we will see what is the relation between different structures. Already I told you, in chain isomers root word will be different, whereas in positional isomers root word is same. Now, if you take this one, always you see IUPAC names to find out what is the isomerism between two given compounds. Butane 1-ol, butane 2-ol. Root word is the same, but they differ in position of alcoholic group. That is why this 1 and 2 are positional isomers. 1, 2. Similarly, you observe this one 2-methyl butane 1-ol. 2-methyl butane 2-ol. Root word is so I made a mistake here. This is 2-methyl propane 1-ol. This is propan-2-ol. Okay. Now you observe this one, 2-methyl propan-1-ol, 2-methyl propan-2-ol. Here also there is difference in position, that is why these two are what type of isomers? Positional isomers. These two. Now observe this. Similarly, 1-methoxypropane and 2-methoxypropane. These are also 5 and 6. These are what type of isomers? Positional isomers. Now observe this, butan-1-ol, 2-methyl propan-1-ol. They differ in root word. So these are chain isomers, 1, 3, 2, 4. Similarly, these two also. They differ in arrangement of carbon atoms. See here all the 4 carbon atoms are in straight chain, whereas here there is a branch. Similarly, here also there is a branch. Then we can write 1, 3, 1, 4. Similarly, 2, 3, 2, 4 are chain isomers. Right. Now, if we take these 3, they have same formula, same functional group, but differ in nature of alkyl groups attached to functional groups. So, 5, 6, 7 are metamers to each other. Metamers. If you observe these two, these are also positional isomers and also metamers. That is, now all these alcoholic structures are functional isomers with these ether structures. That is why we can say that 1, 2, 3, 4, 1, 2, 3, 4 and 5, 6, 7 functional isomers. This is okay. Now if you go in depth, even we can find out in these structures possible with this formula, any isomer shows optical isomerism or not. If you observe that one, already you have idea how to see whether a compound is optically active or not. That later we will discuss briefly. But if you observe this compound, butan-2-ol, you observe this carbon, at second carbon, what is this? This is methyl, this is OH, and this side, this is ethyl group, and what is the other group present at this carbon? Hydrogen. So this carbon is attached to 4 different groups. Then what type of carbon it is? Chiral carbon. Then this compound is chiral compound. Chiral compound means optically active compound. If you include stereoisomers also, total number of isomers possible for this one 8. Total isomers including structural isomers and stereoisomers. Structural and stereoisomers. If we take only structural isomers, we should not take enantiomer of this one, means only 7 isomers. Total number of structural isomers. Seven, like this. Okay. Now we will take one important example. Chlorination of a compound gives how many isomers? That we will check. Now I will take C4H10. How many isomers are possible for monochlorination of this one? Monochlorination means replacement of one hydrogen by a chlorine. For that, first we have to write what are the possible structural isomers of this one, chain isomers of this one. What is this one? Butane. So for butane, how many isomers are there? N-butane and another one isobutane. N-butane. You know, here CH3 is there, CH2, CH2, CH3. Let one hydrogen from this is replaced by a chlorine, monochlorination. So here we will get chlorine. This is CH3, this is also CH3. If hydrogen is replaced from this carbon or from this carbon, we will get same compound, that is N-butyl chloride. Let hydrogen is replaced from this carbon or from this carbon, then we get same compound, that is secondary butyl chloride. Is there any other possibility? No. If it is from this again, we will get same. To know where formed compounds are same or different, you must write IUPAC names, then only you can distinguish. Similarly, here CH3, CH3, CH3. 3 methyl groups attached to a tertiary carbon. These 3 CH3 groups are identical. If hydrogen from any of these CH3 groups is replaced by chlorine, then we will get same compound, that is isobutyl. This one. Here also one hydrogen is there. This carbon is different. This carbon is tertiary carbon. How can you say it is a tertiary carbon? Because it is attached to 3 other carbons, so that is why it is a tertiary carbon. So if hydrogen from this is replaced by a chlorine, then we will get one more compound, that is tertiary butyl chloride. Then total how many isomers are possible for monochlorination of butane? You observe this one. This is a chiral carbon. This is a chiral carbon. This side methyl, this side ethyl, this side chlorine. So one more group is hydrogen. 4 different groups are attached to this carbon. That's why this is a chiral carbon. Then this compound is chiral, that is optically active. So if we take enantiomer, if we include stereoisomers also, including that enantiomer, total number of isomers 5. If we do not include stereoisomers, how many structural isomers? 4. So for this, number of structural isomers 4. That is clear. Now we will take another example. C5H10 will take. Now I will try to write all possible isomers with this formula, including ring isomers also. Okay, this is in accordance with which general formula? CnH2n. So what is this one? Alkene. So what is this alkene? Pentene. But we cannot say exactly it is pentane or any other compounds are possible, later we will see. Okay. First I write 5 carbons in a straight chain, then I place a double bond here, then this compound is pent 1-ene. Now I will shift it to here, pent 2-ene, right, pent 2-ene. Now what I do, I shift 1 carbon to this carbon, then what do you get? A compound like this. I am shifting methyl group to this one. Now I will shift this double bond to this carbon, this one. I will shift double bond to this carbon, like this. So these are possible open chain structures. Then we will see what are the ring structures possible. Here you have to observe one thing, alkenes and cycloalkanes have same general formula. Alkenes and cycloalkanes. So I wrote possible alkene structures. Now I will write possible cycloalkane structures. Then you arrange a ring with 5 carbons like this. I hope that you are understanding this way of writing of structures. Bond line model. We see elaborated structure of this one. It is like this. Okay, this one. Now if you observe 5 carbons in ring and single bonds between carbons, that is why this is cyclopentane. Okay, if you write IUPAC names of all these compounds, later we will see this one. Now I take only 4 carbons in the ring, then there will be 1 methyl substituent. I will take only 3 carbons in ring, then how many carbons have to come out? 2 carbons, ethyl. Then I will write these 2 ethyl groups as 2 methyl groups, then 2 methyl groups at same carbon. Now I will change methyl groups to adjacent carbons like this. Now including ring isomers, total how many are possible? 10 structures are possible. So pent 1-ene, pent 2-ene. Now if we take IUPAC name of this one, 1, 2, 3, 4. What is this one? 3-methyl but 1-ene. And this one, numbering 1, 2, 3, 4. So methyl branch at second carbon. So 2-methyl but 2-ene. Now this one 1, 2, 3, 4. So what is this? 2-methyl but 1-ene, cyclopentane. Now come to this structure, there is a methyl branch. So what is this? Methyl cyclopentane. And this one, ethyl cyclopropane. And this is 1,1-dimethyl cyclopropane, and this is 1,2-dimethyl cyclopropane. Okay, is it clear? So with this you can write 10 structural isomers. Now we will take another example. Okay. C8H10. Observe this. When compared with alkanes, here the number of hydrogen atoms are very less and the number of carbons and hydrogens are almost equal, means there should be an aromatic ring in this one. So, if we take aromatic ring, okay, I will take simple one, that is C7 like this, C7H10 will take. Later we will see higher examples, this one, right. Now, this is one possible structure. What is the name of this structure? Ethyl benzene, aromatic ring. Another compound also I write with aromatic ring, that is a phenyl ring. Now, I split up this into two methyl groups, CH3, CH3. Two methyl groups are at adjacent position, 1,2 position. So, what is the name of this compound? Orthoxylene or 1,2-dimethyl benzene. Now, I will shift this methyl group to third carbon. CH3, and this compound is metaxylene, 1,3-dimethyl benzene. Now, I will shift methyl group to fourth carbon, fourth position, CH3, and this one is paraxylene, 1,4-dimethyl benzene. Now, observe this one, same formula but different structures. Now, if we take relation between this one first compound with other three compounds, what is the difference you find? What is the difference? 1 with 2, 3, 4, they differ in arrangement of carbon atoms in chain. So, chain isomers. Now, if you observe this 2, 3, 2, 4, similarly 3, 4, they differ in position of methyl groups. That is why these are what type of isomers? Positional isomers. Okay, students, I think that you might have enjoyed this isomerism with the different examples. Right, see you tomorrow.